It's a pleasure being here at GopherCon. But before I start my talk, I must say that there is a disclaimer. So today, I feel like speaking about the American civil rights movement with Martin Luther King right there in the audience. So I'm kind of like, and not just one Martin Luther King, but multiple heroes from the whole movement. So, and I'm gonna talk about the roots of Go, the history, and something that I have kind of like traced by myself by reading lots of material and doing some research. So yeah, the roots of Go, okay, or how our past holds the key to the future. Okay, so but before I start, a little bit of motivation. Should I really care about learning history, right? Yeah, you should. Because as Russ said in the morning, right, that if we don't really learn from our past, we are doomed to repeat all the mistakes that have already been committed. We should really focus on learning from history. That way we can avoid the mistakes. Of course, that's one thing. And another thing which is even more important, which I'll try to illustrate today, is that we can then effectively build on top of our past experiences. So it's like additive. You really get to stand on the shoulders of giants. And Go is a great example of building on the past, because Go is absolutely not designed in a vacuum. It's not something that Rob Pike dreamt up one night. It has a very, very long history. Okay? So I expect to illustrate a little bit of Go's lineage today in this talk. But before that, a little bit of segue into the current practices of software development. Right? I would like to visit a very typical software or a language design kind of process. How do we really do that? So we all start really small. We want to build a doghouse, right? So a doghouse is very simple, very easy to build. All you need is a bunch of wooden planks, lots of nails, and maybe a hammer. And you just keep hammering away till you have something which resembles a doghouse. And it works just fine, right? I mean, it's just doghouse. But the problem really crops up when we really succeed in building the doghouse. Because then even your bosses will come and they will say that, hey, you did a good job, so let's scale it now, because we are a VC-funded startup, so we have to scale very fast. We don't really have any time for design. So, and we have already built a doghouse, which is the prototype that we did for demo day overnight. So yeah, and scaling should be easy. So the doghouse was 3 by 3 by 3 foot. And now we want to scale it to 100 by 100 by 100. And should be easy enough. Let's get more wood, more nails, and maybe many more hammers. And let's keep hammering away. Okay? And eventually we'll land up with something which is a cathedral, right? Because that's what we want to build now, because we are VC funded, yo. So yeah. So all you want to do is to basically take something which worked fine in a smaller scale and then apply it in a very large context. But this is what happens, right? What we get instead is a rubble. Because if you really think about it, when you scale a doghouse 100 times, what really happens? The strength of the doghouse, which has been scaled now, goes up by 10,000 times. So because the strength is a function of the area. But unfortunately, the mass is a function of its volume. So it kind of like increases even more. So it goes up by 1,000,000 times. And of course, the strength is not good enough, and it collapses. This is also something that happens very often with our own abstractions, all our APIs, when we build something really small and we try to apply it to a larger context, things don't really work well. But what do we do next? What we do next is even worse. We call it a feature. we claim that we had been building a pyramid all this while. I mean, who wants to build a cathedral? It's so old school anyway. So let's have a pyramid. It's very cool, right? And pyramids have lasted. So one guy actually came up to me and told me that, what's wrong with pyramids? They have lasted for thousands of years. I said, sir, you didn't really get the point. I mean, it's not about lasting because it's just a piece of rock. Of course, it will last. Look at Microsoft Windows for that, for an example. It will last because you just can't move it, right? So it's there. And this is how basically we live in denial. We don't want to accept that design is a very important part of software development. And we should give a lot of importance to design first before we write any line of code. But yeah, it goes on. We rinse, we repeat, we build new tools. Like, I don't have to name them. There are many communities where they're coming up with new build tools every weekend, right? Or a new compiler to gloss over some deficiency in the language itself. We call it iterative development, but it's not really iterative development because we don't really start with a good understanding of the problem. This is what Alan Kay calls it the make and fix paradigm. And that's like really wrong because by taking incremental steps, you can from here maybe you will reach San Francisco, but you can't go to Mars. If you want to take quantum leaps, can't really take incremental steps from where we already are. We have to go back to our past and build on top of that, right? So the make and fix paradigm, and this is how I feel when I look at the overall programming community kind of participating in these kind of activities. So what's the key understanding here? Again, so I'll go back to my guru. He says that at scale, architecture dominates material. It's a very, very important insight, okay? So when you have large scale, it doesn't matter what kind of tools you are using. The architecture is going to matter way more than the tools themselves. Like, for example, if you're building a cathedral, you don't have to use the latest concrete technology. You could still use mud as long as you have your architecture done right. On the flip side, for example, if it's a very small project, feel free to use Ruby on Rails. It's okay. But don't really dream of scaling it one day to something that's really big. I mean, there are many examples right in front of us. We have seen that there are many large companies which have gone through massive rewrites just to be able to serve their users. So yeah, at scale, architecture will always dominate material. Doesn't matter if you are using Go or any other language. If it's a small project, it's probably okay to use Perl. It doesn't matter. Or maybe no thought. I mean, you can just bash it out or bang it out over a weekend. It will work fine. But then don't even think about taking that same thing to production because it will massively fail, right? So architecture, right? It's the practice of the art or practice of designing structures, right? The word architecture comes from arch, which I'll talk about right away, which the Romans kind of invented. So if you look at any large structure, you will see that there is an arch with a keystone on top. Why do we need it? In fact, the arch was one of the key realizations in modern civil engineering. Without the arch, we won't have been able to build large structures without using a lot of material. If you look at large cathedrals, they are very big, but that ultimately very, very little material is used to construct a large structure like a cathedral, because the arch kind of distributes the load equally across the whole building. So yeah, so that's kind of like the background that I wanted to give. But yeah, let's go back to the roots of Go, right? But hey, I won't be talking about the roots of Go today. I'll be talking about the arches of Go, right? So Go, if you really think about Go as a large structure, Go rests its mass on a lot of its arches. So we'll illustrate a few of those arches today. BCPL. So invented by Martin Richards in 67 at Cambridge University. Very interesting. It was invented in 1967, right? And if you really think about it, if you do not know about BCPL, you will think that it's probably some really old and archaic language which is laughable. But let me tell you some of the key innovations that were done in BCPL, right? So BCPL was, first of all, it's a successor to the CPL language, which was also developed at Cambridge. But BCPL was kind of, it's like basic of CPL. It means that they removed a lot of craft which CPL had accumulated over time. And there was a lot of focus on programmer efficiency. How do I make the programmer fast? I don't care about the execution time. It's about adding, making the programmer himself or herself more productive. It was the first language which was a bootstrapped compiler. Go is going to get there soon. We're already there, awesome, yeah. But many languages even today are not bootstrapped, right? So the first bootstrapped compiler, it was byte compiled to a intermediate representation and was ultimately executed in a VM which itself was portable, okay? I mean, and which year are we talking about here? 1967, okay? And BCPL was actually chosen to be the main language for the Xerox Sparks Alto computer, which Alan Kay was also a part of later. And also Amiga OS, a lot of people probably have heard about Amiga OS, which is the OS created initially in BCPL. Some example, this is some example code. This is simple hello world. So the first hello world program was not written in C, it was written in BCPL, as a matter of fact. What are the other innovations that BCPL came up with that Go embodies even today? Look at the comments. These double slash style comments also originated in BCPL. And the most important innovation, I think, that BCPL contributed to Go is the semicolon injection. So if you look at Go's grammar actually has semicolons in them. But as a programmer, we don't write semicolons. Why? Because again, I want to be really productive. So what the lexer does is that the lexer, when it's analyzing the code, it inserts the semicolon at the right places. And so why do I still have to insert the semicolon? Why can't I write a parser which can just parse without semicolons? Well, inserting the semicolons keeps the parser simpler. Again, so then my parsing and my compilation phase is much faster. There are certain problems with semicolon insertion, like in JavaScript, for example. JavaScript also does automatic semicolon injection, but JavaScript doesn't really have any rules about where to put the braces and all these things. So the semicolon can go anywhere, and many times the JavaScript runtime can get it wrong. So as a JavaScript programmer, you are recommended to always put semicolons. In Go, the language designers, they basically just decided that they will have a trade-off, that you have to start that opening brace on the same line. And if you do that, then everything else is taken care of. Then the semicolon injection is deterministic, and there are not much edge cases where it could go wrong. Modular 2, another arch on which Go rests. Modular 2 came out in 1977. It was created by Nicholas Wirth. Nicholas Wirth was also the creator of Pascal. He wanted a successor, a modern successor to the Pascal language, which would again have some innovative features. Let's look at some example code. So this basically just computes the GCD of two numbers in modular 2. Okay. So what did modular 2 introduce, which Go got some inspiration from? The module system. So modular 2 actually was one of the first few languages to have a very advanced module system. And the ideas behind Modula's module system there is a huge overlap between those of modulars and Ghose. For example, inside a Go package, everything is public to the members of that package, right? There is no intra-package kind of protection mechanism. I mean, you don't need that. But everything outside the package will have to be explicitly exported. In modular, you had to do it by using explicit statements. But in Go, we do that by convention. In modular also, it was a convention, but then you had to still use the export statements to export things explicitly out of a package, of a module. But in Go, we do it automatically by just naming public symbols with a capital case. Another thing is the dependency management. Modular 2 again was one of the first few languages which had a very clear dependency management mechanism baked into the language. What does that give me? If you look at traditional systems like C, C++, where we have hash includes, right? And a hash include can also have another hash include, and it's like I'm filling in text. So for the compiler to know about the dependency of any package, it is not really easy. I have to parse a lot of data to know that. And that data is not really stored in the object file efficiently. What modular did was that the exported symbols and other related information that the compiler would need to figure out what other things it needs to compile and link with, that information is available right away in the object. And in Go also we do the same thing. In fact, what they have done is that that data is right, it's aligned in such a way that it's right there at the top. So the compiler doesn't even need to read too much. It can read just a little bit and stop right there. So that's why, again, my compilation is way faster. Okay. So this is again a bonus slide. It shows modular 3. So you can clearly see that how modular 3 is a kind of like an ancestor to Go. The code is already looking a little bit similar to what we have in Go today. Like look at that fumped thing, right? I always had a question in my mind. Okay, why do they call it fumped and not format or something else? Well, of course, because of modular. Because they also called it fumped right there. And yeah, if you look at the type declaration syntax again, it's also quite similar. But yeah, and there are other influences as well, which I'll talk about. Yeah, so next up is CSP. Everyone knows that Go is heavily inspired by the CSP paper by Tony Hoare. So Tony Hoare came up with this paper in 1978. It was a groundbreaking paper. Back then, again, people were contemplating on how to do IPC better. Tony Hoare, just being the bright guy that he was, came up with this idea of basically sharing memory by communicating. Basically, they just changed how we look at IPC itself. The way they solved it was basically by using unbuffered channels as a synchronization as well as communication mechanism. But there were some fundamental differences between the original CSP paper and the implementation that we have in Go today. Let's just talk about that. But before that, a minor aside. The concurrent prime Sieve, a very famous program written in multiple languages over time. Even I'm guilty of writing it myself in Clojure. So Douglas McIlroy came up with this algorithm of implementing a variant of the Sieve of Eratosthenes algorithm of finding all the primes less than n. So the way you do it, the Douglas McIlroy, if you don't know, also invented Unix pipes. So if you read the first implementation that he did, it was just done on plain Unix without any threading or anything. It was just cooperative multitasking using pipes. Initially, he used coroutines, then later re-implemented using pipes. So how does it really work? So what you have here is that you have these processes. They are all daisy chained together. So in the beginning, I basically have a number generator. it generates all the numbers starting from 2 to infinity and sends all the numbers to a process which is right next to it. So the next process picks up the number. The first number that it gets, it prints it out right away as a prime because it knows that by definition that it's a prime. And all the subsequent numbers that it gets, it filters out all the multiples of the first number that it saw and passes them to the next process. So if you just kind of visualize it, if you see that if I have n processes chained together, by the end of the whole processing, I will have a bunch of prime numbers which are all lower than the number of processes that we have. So this is the Sieve algorithm, the same Sieve algorithm implemented in CSP. So CSP, again, it was a paper, but also it was also a kind of like a DSL for writing such kind of programs. So this Sieve algorithm is written in the DSL as designed by Tony Hoare in his paper. So you will immediately see that there are some similarities here. I don't know if you can see, but what I'm doing here is that I'm creating 100 processes right away and then starting all of them and pumping all the numbers through them. So, but then what's the fundamental difference between what we have here and what we can do in Go? The fundamental difference is that channels were second class in CSP. They were not really first class values that you could create dynamically and pass around and return from other functions. But still, CSP was a groundbreaking notion that you could have processes which talk to each other and then it's also kind of a synchronization primitive, so you don't need explicit locks, right? Since the channels are unbuffered, so they will just be parked till there is any data on that. So yeah, that was CSP, and the next pillar, Newsweek, created by Grandmaster Pike, right? So again, Newsweek came out in 1988. It's again an evolution of the Squeak programming language that he, I think, co-created a few years prior. But after Squeak also he created another language called Pan. Pan was not really a programming language per se, it was more like a theorem prover. So if you are writing distributed systems algorithms or IPC kind of algorithms, you could first write your algorithm in Pan and then prove it by running the system. The language Pan adopted is very CSP-like syntax with some extra features on top of it. Yeah, and Newsweek was created for GUI programming because, I mean, you might imagine that GUI programs are really interactive and you need to pass a lot of messages all around. But I think more importantly, what Newsweek really introduced was the notion of first-class channels. For the first time, channels were really first class and you could manipulate them as any value. Okay, and also, again, if you look at this example, so this is Newsweek. This is the same prime Sieve algorithm implemented in Newsweek, and it already looks a lot like Go. Okay, you can see that the type declaration syntax is almost identical except a superfluous off, which we don't write but we say it out anyway today when we read Go code, right? And funcs were called progs, but pretty much everything else is identical, at least as far as semantics are concerned. This is just one half of it, so here I'm creating the counter. And also look at the syntax for sending values to a channel and reading from a channel. It's the same arrow-like syntax. So clearly it originated here in Newsweek. So yeah, that's the counter, and then I have the filter, and this is the main engine which starts the sieve. So you can see that there is this mk function which I'm using to create a channel. We call it make in Go today. And another interesting distinction is that the Go keyword was called begin in Newsweek. And really, thank God that they changed it to Go. Otherwise, we would have been in beginner con right now. And instead of being gophers, we would have all been beginners, which is not really bad. It's like there is a Zen kind of twist to it. Newsweek was also succeeded later by Aleph and Limbo. Aleph was created by Phil Winterbottom, and Limbo, of course, was created by Rob Pike. Yeah. Okay. Next up, we have Smalltalk. So is there any language which is not inspired by Smalltalk? Very few. The Smalltalk basically came up with all the groundbreaking OOPS ideas that we like or maybe do not like as much today. Smalltalk emphasized this whole idea of composition over inheritance and having values as method receivers. So that's also something very interesting. In C++ also we had method receivers, but in C++ all the method receivers were pointer types. In Go, we can have values as method receivers as well. That was also kind of introduced in a way by Smalltalk. And also the whole lack of subtype polymorphism was never really encouraged by Smalltalk guys anyway. And it's no wonder that Go also doesn't encourage inheritance. And then, of course, there are a bunch of other languages and systems like C, Pascal, APL. APL must be the odd guy out here. Of course not. All the three main creators of Go, they all implemented APL back in the day. Robert Grismer, Rob Pike, and Ken Thompson. All of them implemented APL, and of course, it seems that they have certain liking to APL. The iota that we have, the predefined constant that we have in Go, is actually a nod to APL. The type declaration syntax, it might sound weird, but again, it comes from Pascal. In Pascal, type declaration was exactly the same. And of course, the overall surface syntax of Go is similar to C. And why not? Because the creators of Go are also kind of like the granddaddies of C as well. So this is like a very quick kind of genealogy of Go language. Very quickly, you can see that there is a huge influence from the Algol family. Lots of languages from Algol family influenced Go directly or indirectly. BCPL, C, modular, Pascal, Simula. There is a little bit of Smalltalk in the middle. And then on the right side, we have lots of CSP languages. Newsweek, Occam, Aleph, Limbo. All of them influenced Go in one way or the other. And of course, I mean, there is also Lisp right there. So I'm a Lisp guy. I'm a smug Lisp weenie. So yeah, so I mean, I don't think there is any language which was not inspired by Lisp. So Lisp is also there. So what's the key takeaway from here? Why should we really look at old stuff and build on top of the past? I think doing less of the wrong things, it allows us to do more of the right things. So because if you, like Russ talked about in the morning, if you make less assumptions, if you have less coupling, you actually have more flexibility. And it's ultimately more empowering to the programmer. Grandmaster Pike, he summed it up very nicely when he said that less is exponentially more. Like if you implement 10% less, it ultimately allows you to do 100% more. Okay? So yeah, I think let's go forth and build good software. Thank you very much.